Hi, this is Qiaochu at Lehigh University. Today we are going to talk about the homework for week 10. Let's take a look at the first one. What's the difference between the alternate depths and initial or sequent depths? The alternate depths have the same specific energy. One depth is subcritical and the other is supercritical. For instance, let's take a look at the figure 1. Y1 and Y2 are alternate depths. Y2 is in subcritical and Y1 is in supercritical. They share a same value of the specific energy. Initial or sequent depths occur before and after the hydraulic jump and do not have the same specific energy. In figure 2, we can find that the Y1 is a depth occur before the hydraulic jump, and Y2 is the depth after the hydraulic jump. And they do not their corresponding specific energy are different. Now let's move on to the second problem. A hydraulic jump occurs in a 5 feet wide rectangular channel. The initial and sequent depth are 6.66 and 3 feet, respectively. We need to determine first the energy loss, delta E, and the felt number, N sub F, in the channel prior to the jump. First, let's calculate the energy loss. Based on the equation 6.20, the delta E equals to Y2 minus Y1 to the power of 3 over 4 times Y1 times Y2. Because the value of Y1 and the Y2 are given, therefore we can directly calculate the value of the energy loss. It equals to 1.62 feet. Now let's move on to calculate the felt number, N sub F. Because the N sub F it equals to V divided by the square root of G times Y. And we need to know the value of the velocity. To calculate the value of velocity, we can use the discharge per unit width, which is represented by the small q. So based on the equation 6.16, q squared over g, it equals to y1 times y2 times y1 plus y2 over 2. We can bring the value of y1 and y2 into this equation, and g equals to 32.2. Therefore, we can get the value of q. It equals to 10.8 square feet per second. And because the v1 it equals to q over y1, therefore v1 it equals to 16.4 feet per second. And based on the felt number equation, we can get the felt number in the channel prior to the jump equals to 3.56. And because this value is larger than 1, therefore the Y1 is a supercritical depth. Now let's move on to the third problem. So in the third problem, it asks us to construct the specific energy and specific force curves for a 5 feet wide rectangular concrete channel that carries 40 cubic feet per second. We need to use 0.5 feet depth increments up to 3 feet. Now let's solve the energy curve first. Based on the equation 6.8, E equals to y plus the velocity hat, and the velocity can be replaced by q over a, and a equals to b times y. Therefore, we can use this equation to calculate the specific energy. And because the depth ranges from 0.5 to 3 feet, therefore we can list the value of water depth in each section into a table. And then we can calculate the cross-sectional area. Let's use the first row as an example. When y equals to 0.5, the cross-sectional area A equals to B times y. B is 5 feet and y is 0.5. Therefore, A equals to 5 times 0.5 is 2.5 cubic square feet. And then we can calculate corresponding velocity. It equals to Q over A. Q is a constant, is 40 cubic feet per second. A is what we just calculated, is 2.5. So we can use 40 divided by 2.5. It equals to 16 feet per second. So after we got the value of the velocity, then we can bring the value back into this equation. The y is, it equals to 0.5. Velocity is 16. And g is 32.2. Therefore, we can calculate the specific energy. It equals to 4.5 feet when the y equals to 0.5. After we calculated the value of the specific energy in each section, therefore, we can use the Excel to represent the specific energy curve. In this curve, we use the specific energy as y-axis and use the change of the water depth as y-axis. Then we solve the first problem. Next, we need to calculate the specific forces curve. Based on the equation 6.19, the specific force, it equals to force times plus the density times the discharge per unit width times corresponding velocity. And we can calculate the force by using this equation. Gamma divided by 2 times y squared. And discharge per unit width equals to Q over B. We assume that the water temperature is 4 degrees Celsius. Therefore, the specific weight, gamma, equals to 32.4 pounds per cubic feet, and the water density equals to 1.94 slug per cubic feet. Therefore, in this equation, we can directly to bring the value of water depth y and velocity into this equation to calculate the specific forces. The velocity is what we just calculated based on in the previous steps. So after we got the value of the specific forces in each section, therefore we can make a plot like this. And y-axis represent the water depth and x-axis represent the specific forces. Now let's take a look at the problem 4. The problem 4 is related to the classification of the graduate varied flow. There are 4 scenarios in our homework. Let's take a look at the first scenario. There is a flow move from a steeper channel to a steep channel. The step 1 to solve this problem is to draw a critical depth y sub c and the normal depth y sub n. Let's draw the y sub c first because it doesn't change with the slope, which is represented in green. And because it's a steep slope, the normal depth should lower than the critical depth. And the normal depth in a steeper channel should lower than the normal depth in the steep channel. Therefore, we draw the normal depth in orange line. The step 2 is to try y, the water depth, actual water depth y close to the normal depth at the far end, which is represented by a green dot. The step 3 is to draw the water depth. Because we know that the blue dot here, which is represent y, is lower than the critical depth. So therefore, there is a supercritical flow. Similarly, in a steep channel, the green dot is also lower than the y sub c. Therefore, it's also a supercritical flow. For a supercritical flow, the transition of the slope only affect the downstream. Therefore, we'll leave a space at the downstream here. The next step is to complete the segment to fill out the space here. Is because the starting point of the transition, which is represented by the orange dot here, its location is lower than the normal depth and the critical depth. Therefore, is at the section 3. The dy over dx should larger than 0, which means that the flow after the starting point, the orange dot here, should increase along with the channel until it approaches to the normal depth. In scenario 2, we have a flow move from a milder channel to a mild channel. Similarly, the first step is to draw a critical depth. And because there is a mild slope, the critical depth should lower than the normal depth. Then our normal depth should higher than the critical depth. And the normal depth in the milder channel should higher than the normal depth in a mild channel. Next, we need to try the actual water depth y. It close to the normal depth at far end. In the plot, we use the blue dot to represent the actual water depth at far end. And then we can draw the water depth because the elevation of the blue dot in a milder channel is higher than the critical depth, and there is a subcritical flow in a milder channel. Similarly, the blue dot in a mild channel is also larger or higher than the critical depth. So we have subcritical flow in both two sections. Because for a critical depth, the change of the slope only impact the upstream. Therefore, we leave empty space here. The next step is to fill out the empty space. Because at the transition point, which is represented by the orange dot, its location is in the middle of the critical depth and the normal depth in the upstream. Therefore, the curve should follow the type 2, which means that from this point, the water depth should decrease along with the channel until it approaches to the transition point. In other words, the dy over dx should smaller than 0. In the third scenario, the water moves from a steep channel to a steeper channel. Similarly, the first step is to draw a critical depth. And then we can draw a normal depth. Because it's a steep slope, the normal depth should lower than the critical depth, and the normal depth in the steep channel should higher than the normal depth in a steeper channel. The next step is to try the actual water depth close to the normal depth at far end or control. So we use the blue dot to represent the actual depth at the far end. Then we could draw the water depth. Because the location of the elevation of the actual depth, which is represented by the blue dot, it's lower than the critical depth. Therefore, there are a supercritical flow in both two sections. So for supercritical flow, the transition of the slope only impact the downstream. Therefore, we leave an empty space at the downstream. The next step is to fill out this empty space. Because from this transition point, the orange dot here is, this orange dot is in the middle of the critical depth and the normal depth in downstream. Therefore, the water move after the transition point should follow the type 2, which means that the water depth after the transition point should decrease along the channel. In other words, the dy over dx should smaller than 0 until it approaches the normal depth in a steeper channel. In scenario 4, the water moved from the lake on the left-hand side to the lake on the right-hand side. There is a sluice gate in the middle, and the gate is on the top of the steep channel. The first step is to draw the critical depth, which is represented in green line. And because it's a steep slope, the normal depth is lower than the critical depth. Then we can draw a line, the orange line, to represent the normal depth. After that, we can assume that the actual depth at the far end is close to the normal depth. And because in this scenario, we know the depth before the gate and the depth at the bottom of the gate, so we can add these two points as a control point. After we have the two control point and the actual water depth at the far end, then we can draw the water depth. So the next step is to complete the segment. After the water moves from the lake on the left-hand side, it should approach to the normal depth. And because the elevation at this point is lower than the critical depth, so there is supercritical flow. And because at this point, its location is higher than the critical depth, then there is a subcritical flow. So the transition from a supercritical to a subcritical flow, there should have a hydraulic jump in the middle of these 2 points. So after they have a hydraulic jump, the water depth should increase to approach the water depth before the sluice gate. So after that, let's take a look at the control point at the bottom of the gate. After the water moves from the bottom of the gate, because at this point is lower than both the critical depth and the normal depth. So after the water move from this point, it should follow the type 3 to approaching the depth, the normal depth, and then connect it to the lake on the right-hand side.